Hello, everyone. Thank you so much for coming today. My name's Chris, and I'll be presenting today on behalf of the Mechanical Subteam. First and foremost, what does the Mechanical Subteam do? Famously, we design, manufacture, and test the structure of the CubeSat, which you've seen multiple times before tonight. We also make sure that every other subteam can successfully interface with the CubeSat. We assemble it all together, we incorporate the deployment mechanism, and we make sure that we interface properly with the NRCSD, or the NanoRacks CubeSat deployer, up on the ISS, which we'll all talk about a bit today. Here's a look at the team. We're a very specialized team, all from mechanical engineering, as you can see, and Adam from engineering physics. We're a close team, and we all get everything done on time. Moving on to the spacecraft design. This is what a render of what it would look like up in space. Obviously, this isn't to scale or anything, but just a nice render. And on the right, you see the satellite all combined and assembled. Moving on to the structure, which is what I mentioned earlier. This is the main portion of what we do in mechanical. This entire structure is comprised of 2 identical rails that are vertical and 3 horizontal support trays. Everything is designed by students in-house, and we hope to manufacture as much as we can on our own. The main purpose of this, although it makes sense that we need to make sure everything stays within the structure of the satellite, we have to make sure that we survive launch. If we don't survive launch, then we can't deploy and we can't start collecting data, which is the main mission purpose. As well, we have to mount all of the components, which is why you see so many different holes all over the place in the rails. And we have to interface with the deployer, which is why we have so many specific dimensions and a certain shape. Assembling the satellite seems like it would be complex, but we have it in a pretty straightforward way. We've made it very modular. So the satellite can be broken down into 3 kind of modules, where you see the payload, the bus stack, which is a combination of all of the PCBs from the other subteams that we were speaking earlier. The rest of the structure comes and closes it all together, and then we have what you've seen so much before. So it is straightforward, and we hope to keep it like that when we get to assembling in the future. The bus stack is one of the other portions of the satellite that mechanical is in charge of assembling. Like I said, it incorporates every other PCB, which are all listed here, as well as 2 other pieces of the structure, which is why they are not included earlier. A lot of testing has to be done to the structure in order to make sure that it can survive launch, which is one of the main forces that we'll see, and we have to survive. During launch, we expect to see a range of 0 to 2,000 hertz, and we have to make sure that when we design the structure, that its first mode isn't at 2,000 hertz or within this range. If that were true, then we would see resonance, and we would see a lot of fracture, and we would see a lot of deformation in the structure, and that would cause a lot of damage to the interior parts. Here you can see 3 of the first modes, and we've successfully designed a structure incorporating the payload housing that does not or will not experience this. Another one of the most in-person testings that we're going to do is with the vibration plate. Here you can see the structure with a bunch of dummy masses inside, simulating the mass of all of the internals, as well as where we would put the accelerometers to measure the acceleration experienced. Here we're going to confirm our simulations, and we're going to see if we can make any changes or improvements to the structure. The NRCSD is where we deploy on the space station. I mentioned it earlier, and it's what we have to interface with properly. I mentioned that if we can't survive launch, then we won't be able to deploy. Well, if we were not able to deploy, that's another way that the mission will fail, and we won't be able to collect data. Here, you can see an astronaut on the ISS assembling the NRCSD. Now he's putting up the mounts, and then you'll see him soon. Here he is putting the NRCSD itself up on the mounts. The satellites themselves are actually sent up in the rocket already inside the deployer. That's why you don't see him putting anything in it just yet. Behind him, that tube that it's going in, that's the JAXA airlock. So you'll see him slide it in on the rail on the right, and then obviously it depressurizes and it's stuck outside of the ISS so it can deploy. An example of deployment is we're going to see right here. It doesn't really show the rest of the ISS. You can see a bit of the Canadarm, and that's a deployment. It's a lot of fun to watch, and hopefully that's going to go smoothly for us. But that's just an example of what it'll look like. Specifically, though, the NRCSD mechanically and electrically isolates the CubeSat. So it'll be onboard power, it'll be offboard power, which ISS power, and then the NRCSD will help to make sure that everything goes internal and that the CubeSat is working fine on its own. The way that it isolates electronically is with these deployment switches, is another thing that Mechanical is in charge of. Here you can see two slots, which you might have noticed before, in the rails of the in the rails themselves. So these rollers stick out through these holes, and they interface with the rail of the NRCSD itself. So when it's deployed and shot out, the rails untrigger, and that sets the internal power system running on its own. And the solar panels that Michael mentioned earlier start feeding power into the system. That's all I have today. Thank you so much for coming. If you have any questions, feel free to visit Patrick and me in the booth later on. Thank you.